So we were seeing that in the electric field of this capital Q charge, which is a positive, we are bringing this small charge from R to P, and we are working with a force F external, and as soon as this reaches to this point P, so a potential energy is stored because of the work done on this charge, and we remove this F external charge, F external force. So as that external force is removed, this electrostatic force will try to remove it away, this small q charge to away, and the potential energy stored in this charge will be converted into kinetic energy in such a way that the sum of kinetic energy and potential energy remains conserved, because this is a conservative type of force. So this is the whole thing what we are trying to say. So let us calculate the work done in moving this charge from R to P. So moving this charge from R to P is F external into small distance dr, and moved from R to P. So this is the work done, and somewhere here it is written that F external is equal and opposite to electrostatic force. So same thing they have put here. So moving from R to P, and this F external is changed with this F electrostatic dr. So this is work done from moving R to P is simply minus of this from R to P F of electrostatic force into dr. Now what is this? So remember, when we last year we did similar kind of examples. So the work stored delta W was F dot dx. You remember that it was F dot dx. A very small work done. Very small work done and moving in a very small distance due to a force F. Now again, so what we did, so total work done was, let us say 0 to x naught, and this was F dot dx. So similarly here, so instead of moving from 0 to x naught, we are moving from R to P. This F is replaced from electrostatic force, and this dx is replaced by simply dr, very small distance. So this is work done is moving this charge from R to P. So in a way, so we can calculate the work done in moving this charge from R to P. Now this work done is against the electrostatic repulsive force and get stored as potential energy. So that we had already talked about, and since this is working opposite to the repulsive force, it will get stored as potential energy and will convert into kinetic energy in such a way that total of both the energy will remain conserved. Now at every point in electric field, so this is a very important point, at every point in electric field a particle with charge q possesses a certain electrostatic potential energy. This work done increases its potential energy by amount equal to the potential energy difference between points R and P. So let us understand what they are trying to say. So let us say this is earth, and there is a small ball on this earth. This is on the surface, this is on the surface of this earth. So forgive my drawing, it is not very good, but try to understand the concept. So my drawing is not very good. So the ball is on the surface of earth. So as if a person comes here and the person lifts this ball up from here to here. So you say that it has acquired some potential energy PE. Potential energy PE. So what they are trying to say in this statement is PE is never equal to 0. So we never say that this potential energy is absolute, because there is no zero potential energy. Why? Suppose if we take this case, so this is the center of earth and this is the center of this ball. So even in the gravitational theory, we consider that both of these must be point particle, but in reality these are not point particles. So the distance between them is not 0. The distance between 2 points must be 0, but there is a distance which is equal to radius of earth. So even at this point, this ball has some potential energy, P1 equal to mg re, the radius of earth. Okay, so even at this point, this has some potential energy. Now at point P2, what is the potential energy? mg re plus the height of this, let us say h, mg h. Now what you say, you never say the potential energy stored in this ball. What you are trying to describe is the potential energy difference. So the potential energy difference, delta P, is simply mg re this P2 minus P1, P2 minus P1. So if you do this math, so this and this cancels out, and only remaining energy is mgh. So in a way, there is no absolute potential energy. What you measure always is the difference between potential energies. So similarly to the gravitational field, in electrostatic field there is no zero potential energy. The charge q possesses a certain electrostatic potential energy everywhere, at every point. So at every point, so this was capital Q, this was small q, and you are bringing it from R to P. Even at R, it has some potential energy which could be P1. At this point it is P2. So only potential energy you are talking about is the work done or the difference in the potential energy. So work done must be stored as difference in potential energy, that means this. So what they are trying to say is you always measure the difference, not the absolute potential energies. Okay, so this was the whole point. Now let us see some important points. Note that this displacement is in opposite sense of electric force, and hence work done by electric field is negative. So what they are trying to say, so note that this displacement is in opposite sense to the electric force, hence work done by electric field is negative. So we are moving the particle, in this sense, and this electric field is outward and the particle is coming inward. So the work done by the electric field is negative. So because we are moving particle in this direction and electric field is working outwards, so the work done by electric field is always negative. Now therefore we can determine electric potential energy difference between 2 points. So as we discussed, so we always determine the difference between 2 points as the work required to be done by external force in moving without acceleration. So if we calculate this work done in moving, any charge particle from R to P can be any 2 point, so we will be able to calculate the potential energy stored in that particle. Again, there must be no acceleration, without acceleration. So that means force applied is only that much that it cancels out the effect of electrostatic force. It should not be more than that. Okay. Now charge q from one point to another point for electric field for any arbitrary charge configuration. This is what they are trying to say. So we can do this for 2 positive charges, 2 negative charges, or 1 positive 1 negative charges. We can do this. Now let us see this some comments. 2 important comments may be made at this stage. So this is equation 2.2. The right side of equation 2.2 depends only on the initial and final position. So what they are trying to say, it is dependent on P and R. Okay. It means that work done by an electrostatic field moving a charge from one point to another depends only on the initial and final position, and is independent of the path taken from it to one point to another. What does that mean? So let us understand this thing, that why it is path independent.